Good morning all. Cauchy stress formula or stress components in an arbitrary plane. In advanced mechanics of solids, for the KTU subject for S4 mechanical engineering students, ME202 advanced mechanics of solids, we are having a term Cauchy stress formula. Cauchy stress formula is an important topic in the subject. Prerequisites to learn Cauchy stress formula are 1. Cartesian coordinate system and direction cosines, 2. State of stress at a point in Cartesian coordinate system, and finally 3. Stress tensor at a point. We all know what is Cartesian coordinate system, x, y and z axis systems. Then state of stress at a point is defined by stress tensor. Before going to the stress tensor, consider a cubical element as shown in the figure. There will be 6 faces for the cubical element. On each faces there will be stress components along x, y and z direction. In the rightmost plane there is a normal stress component sigma xx and 2 tangential stress components sigma xy and sigma xz. Similarly, along all other planes there will be normal stress components and tangential stress components. So finally these stress components defines the state of stress at a particular point. Stress tensor. State of stress at a point is defined by 9 components of stress, which is defined in the matrix form as shown in the figure. That is sigma ij is equal to sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz. This type of representation of state of stress at a point is known as stress tensor. That is, the representation of state of stress at a point in matrix form or tensor form is known as stress tensor. Usually stress tensor is of rank 2. Rank 2 came because of the values of 2 variables tau ij. I and j will be having xy or z, xy or xz or yz like that. So since 2 variables defines the stress components, it is known as rank 2 tensor. Also from the elementary mechanics of solids, we know that complementary shear stress theory, and complementary shear stress theory states that tau xy is equal to tau yx, tau xz is equal to tau zx, and tau zy is equal to tau yz. Derivation of Cauchy stress formula. Components of stress vector on an arbitrary plane. So finally Cauchy stress formula deals with the components of stress vector on an arbitrary plane. How to find the stress components when state of stress is defined by a stress tensor. Consider an inclined plane ABC at the same point P where the state of stress is defined by the stress tensor sigma j. That means already the state of stress at a point P is defined by a stress tensor sigma ij. That is, we know the values of sigma xx, tau xy, sigma yy, tau yz, sigma zz, tau zx, etc. Let the normal of the plane ABC is n, unit vector n, and its components nxi, nyj and zk. According to the definition of direction cosines of the plane with the normal n is nx, ny and z. These nx, ny and z values are known as the direction cosines. We have to find the resultant stress vector on this arbitrary plane ABC. Let Tn be the resultant stress vector, or it is also known as traction on the plane ABC. So the traction or resultant stress vector will be having 3 components along the x, y and z directions, and it is notated as Tnx, Tny, Tnz respectively. Let delta A be the area of plane ABC. If area of the inclined plane ABC is known, we can find the projection of that area on XZ plane, YZ plane and ZX plane. So it will be obtained by multiplying the area of the inclined plane ABC with the respective direction cosine value of nx, ny and nz. So here OBC or PBC is equal to delta A into nx, PAC is equal to delta A into ny and PAB is equal to delta A into nz. Now after knowing the basic formulation and basic assumptions, we are going to apply the force equilibrium to this triangular element or prismatic element. So considering the force equilibrium along x, y and z directions, we can derive the corresponding components of traction along x, y and z direction respectively. Force equilibrium along x direction is, we know the component of traction T and x in x direction into that area will give the force in x direction, and which will be equal to the sigma xx into delta A into nx, where delta A into nx is the projected area on which sigma xx is acting. Similarly, tau xz into delta A nz plus tau xy into delta A ny. So these values, the sum of these values will give the net force along the x direction, and which will be equal to the Tnx into delta A. Similarly, after that, cancelling delta A on along the delta A on both sides of the equation, you will get Tnx is equal to sigma xx nx tau xz nz tau xy ny. Similarly, we can find out Tny is equal to sigma yy ny plus tzy nz plus txy, tau xy nx, and Tnz is equal to sigma zz nz plus tau xz nx plus tau yz ny. Finally, we have a series of equations, and the component of traction vector along x direction Tnx is equal to sigma xx nx plus tau xy ny plus tau xz nz. Tny is equal to tau xy nx plus sigma yy ny plus tau yz nz. Tnz is equal to tau xz nx plus tau yz ny plus sigma zz nz. These three set of equations are known as Cauchy stress formula. Finally, Cauchy stress formula will give the stress components on an arbitrary plane with the direction cosines nx, ny and nz. By knowing these stress components, we can find out the net stress vector acting along that plane and its direction. If Tn is the resultant traction vector or stress vector on a plane ABC, then we have, according to three-dimensional geometry, Tn square is equal to Tnx square plus Tny square plus Tnz square. That means squares of the components will give the square of the resultant vector. If sigma n and tau n are the normal and tangential components of stress vector or traction on the plane ABC, then we have normal vector square plus tangential vector square will give the resultant vector Tn square. Okay. Normal components of stress vector traction is the projection of vector Tn along the normal end. So to find out the normal component of stress vector Tn, we have to project the vector Tn along the normal vector, which will give the normal component of stress traction. So instead of doing that, we can do we can project the components of traction vector along the normal. So finally, sigma n is equal to nx into Tnx plus ny into Tny plus nz into Tnz. That means the components of traction vector Tnx, Tny, Tnz are projected along the normal of the plane, and which will sum up and which will provide the final value of normal stress vector on plane ABC. To find the tangential stress vector tau n, tau n, we have the equation tau n square is equal to T n square minus sigma n square. So by this much data we are arrived at an important set of equations known as Cauchy stress formula. By this equation and by the knowledge of these equations we can find out the stress vector acting on any plane, and we can find out the normal component of stress vector on that plane and tangential component of stress vector on that plane. So let us go to the solution of a problem. A rectangular steel bar having a cross section 2 cm into 3 cm is subjected to a tensile force of 6000 Newton in the axial y direction. Determine the normal and shear stresses on the following planes whose direction cosines of the normal is given below. So finally how the bar is loaded is given and the cross section is given. So load divided by cross section area will give the axial stress, and it will be sigma yy, and all other stresses are, there exists only an axial stresses, the other components of stresses are 0. So we can formulate the stress tensor at a particular point, and after knowing that stress tensor we can find out the stress vector on any other plane if its direction cosines are given. Here direction cosines of 3 planes are given. So applying Cauchy's formula of resultant stress, we can find out the normal and tangential stress acting on these 3 planes. Try to solve it.